Hi, my name is Joshua Fuller, and today I will be teaching you about trig substitution. Trig substitution is looking at integral equations and recognizing certain forms within them, and then substituting trig functions. And that might not make sense now, but it will after I do a couple demonstration problems. So let's look at this one right now. The integral of 9 over 1 minus x squared. There's a little something funny about here. It looks really familiar. Let's go back to our little sheet over here. Hey, it's just this. And so once we recognize that form, we can substitute in sine the corresponding trig function. So let's do that. Let's just say we're going to have x equal sine theta, and dx, because you can't forget that, equals cosine theta. Now let's just rewrite it. So we can move the 9 outside of the integral, because it's just a constant, and rewrite it as 1 over 1 minus sine squared theta times cosine squared theta d theta. Well, again, recognizing form, this 1 minus sine theta is just equal to cosine squared theta. So we can rewrite it again. Let's move down. 9 integral of cosine theta, because we can just move that over cosine squared theta d theta. Well, that's really easy. Now we can just cancel this squared, and we cancel this out. Simplify yet again. 9 theta of 1 over cosine theta d theta just equals 9 integral of secant theta d theta. And now we just have to take the integral of secant, which, if you remember, let's put the 9 out front again, is equal to ln of secant theta plus tan theta. Boom. But we have an issue. If you look back up here, we're solving for x. We're solving for x, and right now we're in theta. So now we have to substitute. We have to figure this out. So x is equal to sine theta. Well, what if we just switch this around? What if we just say that theta is equal to the inverse sine of x? That makes it really easy. If we draw a little triangle, we can see that, well, sine theta equals x. Sine theta technically equals x over 1. So you can represent that as, draw a better triangle, a straighter triangle than that. It's really a sine of x over 1. And that's opposite over hypotenuse. And using the little Pythagorean theorem, we can figure out that this equals 1 squared, technically, minus x squared, which looks really, really familiar to the top. Whoa, boom, 1 minus x squared. So we can use this handy-dandy triangle to solve for secant theta and tan theta. So now we have 9 ln. Well, secant theta, secant is hypotenuse over adjacent. If we just reference our little triangle, we get 1 over 1 minus x squared, plus, and tangent is just opposition over adjacent, and so we get x over root 1 minus x squared. Boom. That's our answer. Let's move on. Okay, so let's look at this problem here. Now, again, the first step with this thing is recognizing the form. And there's something that looks awfully familiar about this. If you remember from 2 slides ago, you'll see that this is the same as tangent. So let's just substitute in x for tan theta and dx for secant squared theta. But there's a problem. if we were to substitute in tan theta for this, we would get tan theta squared plus 4. But the form doesn't allow for plus 4. If we were to try to solve for secant there, it wouldn't work. So we have to do a little gerrymandering here. Let's just, for fun, add a 2 in front of this tangent. And then, since this is the derivative, add a 2 there. Now when we square it, we'll have a 4 tan squared theta plus 4. We can just factor out a 4. So let me show you how we would rewrite this. So 2 tan theta square root times the square root of 4 tan squared theta plus 4 times 2 secant squared theta d theta. Now this may look like we made it way more complex, but we actually didn't. So let's simplify a bit. Let's move the 2 over here, and let's simplify this entire expression with a new color. The integral from 4 tan theta secant theta, so times, and this would be the square root of 4 tan squared plus 4. If we factor out a 4, we get the square root of 4 tan squared plus 1, tan squared plus 1 equaling secant squared theta. So we can simplify it down to 2 secant, 2 secant theta. And so let me just rewrite that. So we would have 4 tan squared theta plus 1. This equals secant squared. And from that we can simplify it down to here. D theta, of course. So now, this also looks like an unusable form. But it's not really. It's not. Oops, we forgot a squared over here. It's not really. Now we have to use one of our old friends, U substitution. I'm going to use gray for U substitution because I don't like it. Looking at this, we can see that, well, the derivative of secant is tan secant. So let's just assume that U equals secant. Let's just use that. U equals secant theta, du equals tan theta secant theta. That actually makes it really nice. If we simplify again, this whole thing is simplifying. We move this 2 over here. We substitute in u for secant, and then du for this tan theta and this secant theta. Well, we get the integral of 8 u squared, because this is u, du. Of course, there's a d theta over here. Well, that just made it infinitely times easier. Then we have an 8 integral u squared du, which is just equal to 8 times u cubed over 3. Substituting u, and so we substitute in, secant theta as u, and boom! Problem part 2. This is in theta. We don't want it in theta, we want it in x. So we have to make that handy-dandy triangle again. Boop. So up here, all the way up here, we said that x equals 2 tan theta. Well, that's really like saying tan theta equals x over 2. Well, tan theta is just, opposite over adjacent. Throw this in up here. X squared plus 4, which I will remind you looks a heck of a lot like our original problem, as it should. Substitute this in. 8 thirds times secant cubed. Well, secant is just hypotenuse over adjacent. And so we get this big parentheses, x squared plus 4 over 2 cubed. Boom. That's our answer. Sure, you could simplify it more, but Thank you for listening to my presentation, and I hope you enjoyed it.